basis towards the end, but it's the same principles that we've talked about up until this point. We're dealing with principles of equilibrium. We're just now using it to explain solubility. And we'll do the same thing with acids and bases, right? So you've learned earlier in previous classes that a compound is considered what if it dissolves in water? How would you describe that? Soluble if it dissolves in water, or if it dissolves in any solvent. And it's insoluble then if it doesn't dissolve. And the solubility of an ionic compound could be better understood by understanding the principles of equilibrium. Right, so this is what you guys did last week with your potassium tartarate, right? You determined the molar solubility and then also the solubility product, right? So if we have some reaction or some process, right, we have a solid and we want to dissolve it, right? What dissolving it means, so this is a solid. We add to water in this case, and then it puts it in the aqueous phase, right? And all the aqueous phase means is that it's solubilized by water molecules, right? This is what it means for it to dissolve in water. Especially if we have an ionic solid like this one, it'll dissociate the ions, right? So we have two fluorine atoms that get dissociated into two fluorine anions. And then we only have one calcium cation, so we have a stoichiometric coefficient of 1 there. And so these ratios are determined by the preferred charges of each of these anions. And what happens as they get in water, if we have a calcium with a positive charge that looks like this, then we have a bunch of water molecules, and they all gonna have a partial negative charge on them. Something like that. And they're attached to a bunch of hydrogen. But the molecules will orient themselves if it's around a cation. And then if it's around an anion, it'll be opposite to that. So we're looking at going from something that's a salt crystal to then when it goes in water, it gets surrounded by water molecules, and that's what we mean when we say it's the aqueous phase. And the reason for that is because we create a shell of water molecules around the cation like that, so it kind of moves through the liquid as if it's part of the liquid, right? This is what it means for it to be dissolved in solution. And so we can understand how much is going to be dissolved in solution by understanding equilibrium, right? So we can write a chemical reaction like this, and even though this is not a chemical process, this is a physical process, we can still represent it in terms of equilibrium, right? And so this equilibrium reviews solubility as a process that's reversible, right, which is one of the requirements for equilibrium, means that it can go in both directions. And the amount of precipitate or amount in the aqueous phase tells us the extent of this solubility of that compound, right? And so if we had an equilibrium constant for this reaction, how would we write that? Right, it's called KSP, right? So KSP stands for the equilibrium constant or the solubility product. That's what the SP stands for, the solubility product. What would the equilibrium constant for this process be? So this is exactly the same as any other equilibrium reaction that we're looking at. It's a physical process this time because it's dissolving this ionic solid. But the equilibrium constant is the same, or it's the same idea. What is the equilibrium constant in general? Products over reactants, the concentration, and over reactants. And so what would that be for this reaction?
Ca times F squared over
Yep.
CAF2.
Ca 2 plus F minus squared because it has a coefficient of 2. And then do we put over CaF2?
Oh, it's a solid.
It's a solid, right? Which means that we don't care about the solid here, right? This is a solid, and so that doesn't go in our expression for equilibrium. So now you can see why this would be useful to determine it this way. That means that if we get an equilibrium value for this, this is going to be related to directly how much dissolves in solution when we put it in, right? We initially have solid, and we have some water. We throw the solid in the water. That's your initial mixture before it reaches equilibrium. And then once it reaches equilibrium, it's related to this solubility product, right? So this is directly going to be telling us how much of it actually dissolves in solution. All right, that's because solids are not included in our equilibrium constants. And this is, Kc, Kp, and now Ksp is the same thing. And so this Ksp is a measure of the degree of the solubility of the compound. So here are some typical values for some ionic solids, right? So almost all of these, we have a metal with some counterion. Either that counterion is a single element like sulfur, or it can be a polyatomic ion, right? So that's this ionically bonded to each other, and it gives you a value. You see the values are all generally relatively small. On the upper end, it's like 10 to the minus 5, right? That's because in general, when we want to reach a saturated solution, right, it depends on the specific ion and how well that solubilizes in water. And so for certain ionic compounds or certain cations and anions, those will be more soluble than others. And we can look at the size, the relative size of these exponents, and that gives us an idea of how soluble that will be in water, right? So if we have something that's very, very small, right, in terms of our equilibrium constant, what's favored at equilibrium? The reactants, right? And in our case, the reactants are what? The solid, right? So the reactants are the solid, which means that if K, right, the magnitude of Ksp tells us how soluble something is, the smaller this value is, right, the more reactants we have in this case. So is that going to be something, bless you, that's more or less soluble, you think? Right. K is products over reactants, right? We don't include the reactants in our expression, but the relative magnitude of that equilibrium constant tells us the same thing. So if we have something like 10 to the minus 29 here, do you think that's going to be soluble or insoluble? Right? If this was our equilibrium constant for normal reaction, what would you say is favored? Reactants or products? It should be the reactant, right? And so all of these are going to be smaller than 1, right? So technically they're all reactant favored, but if we're comparing them to each other, this means that the reactants are really, really, really favored in this reaction, right? Which means that we're going to favor which phase, the aqueous phase or the solid phase? The solid phase. So do you think that means it's more or less soluble if we favor being solid? It'll be less soluble, right? So the smaller Ksp is, the smaller Ksp, that's the less soluble. The larger Ksp, that means it's more soluble. And so we can understand that just by thinking about what the equilibrium constant in general means. Right, so that's why it's useful to think about solubility in terms of this. Even though it's a simplified physical process, it's not a chemical reaction that's going on, it's useful to think about it like this, right? Because initially when we put a solid in water, it's out of equilibrium, it reaches equilibrium, we want to know what that ratio is at equilibrium. And that ratio, which is really just the product of the concentration of the products, tells us how much is actually dissolved in solution. And so this value is related to the molar solubility. Does anyone remember what the molar solubility is from lab? So the molar solubility was the maximum moles of solute we can dissolve in a given volume, right? So this will be in either units of grams per liter or moles per liter. Right, so when we did the potassium tartarate lab, we made a saturated solution, right? So when we calculated that concentration, we knew that that was the molar solubility. How? Because we tried to dissolve too much, what we knew was too much in the water. We filtered out the excess solid, and then we calculated the concentration of what was left over using the titration. And so that was useful because that's related to KSP for the physical process of dissolving that solid. In that case, it was potassium tartarate. And so they're not generally used to compare molar solubilities, right? Because they're not a one-to-one thing. It really depends on the stoichiometry of the reaction, right? So for example, if we have these two compounds, their KSP, something like 10 to the minus 13 and unitless, their molar solubility is in units of moles per liter or grams per liter, is going to give you a different value. So comparing them to each other are not exactly the same thing, right? So if we look at these two, the KSP is, going up in value between these, but the molar solubility is actually going down between these two, right? So we can't compare the KSP between two different substances with the solubility of those two different substances. And that has to do with the dissociation of the reaction, right? Because the molar solubility is going to depend on the stoichiometry, right? So what I mean is going to have it's only comparable if it has the same stoichiometry, right? So if we have these two here, now they're going to follow a similar trend, right? Because they're going to have the same stoichiometry. So how do you know what the stoichiometry is for these different reactions? So this is kind of bringing us back to first semester general chemistry, right? How do you know what the stoichiometry is going to be for these ionic solids when they dissolve? All right, let's look at the example of magnesium hydroxide. What will be the products on this side? All right, so we're going to take MgOH. This is our solid, right? So this is why, if we're making a base usually, you start off with some solid salt crystal. We add it to water. What are the products going to be?
Magnesium.
Yep, we're going to have magnesium. It's going to be aqueous, right? Because it's a cation that's going to be dissolved in the solution. What's the charge on that? Two plus. So how do you know that? How do you know that magnesium is going to have a 2 plus here? Harley? Yeah, because of the subscript, right? So we have 2 hydroxide. Each hydroxide is -1, right? Which means to counteract that, to make a neutral ionic compound, we need to have 2 plus to counteract 2 -1s, right? And so then the coefficient will just be 1 there. What about for the hydroxide?
2OH.
It'll be 2OH minus, and that'll also be aqueous, right? So this will give us 2 hydroxide ions. Right here we see where the subscript comes into play, right? That gives us the stoichiometric coefficient here. So if we compare these two, the molar solubilities in the KSPs follow the same trend because they have the same stoichiometry, right? Because if we look at the solubility product, which we'll do in a second, well, that depends on the stoichiometry, right? Because this goes into our equilibrium expression. And so, excuse me, if we look at that compared to the previous page here, right? What's our two products for iron here? We have iron carbonate. CO3, sorry, bicarbonate. This one, maybe we don't remember our polyatomic ion, but what will this give us? Fe aqueous plus CO3 aqueous, right? What's the charge going to be on iron? It should be positive 2, because bicarbonate has a charge of 2 minus, right? So our coefficients are each going to be 1 here, right? So if we look at this and compare it with the magnesium hydroxide reaction that we just looked at, this gives us a 1-to-1 of each ion in solution, whereas this one gives us 1 and 2, right? That's what we had here. So that's what's giving us the difference between the trends in molar solubility and the solubility product, right? So these are only going to be directly comparable when the stoichiometry of the reactions is the same for what you're comparing. In terms of solving problems and whatnot for determining concentrations or molar solubilities, that's not really going to change how much. This is just why sometimes you'll see that these trends are opposite to each other. It's kind of similar to when we looked at Kp and Kc. There were certain scenarios where they would predict different favorability of products and reactants. So what would the solubility product be for this reaction or this physical process? Or so why don't you guys write the equilibrium constant for that? What is KSP for this?
Mg times OH squared.
Yeah, we have magnesium ion, and then our hydroxide, and that's going to be squared, right? Because we have the coefficient, which is why that's going to be squared here. All right, so this concentration for a saturated solution would be the molar solubility. The solubility product is the product between both of these. All right, what about for the dissolution of calcium phosphate? What would be the molar solubility for this? What is the solubility product for this reaction. Calcium 3 plus, or sorry, 2 plus, to the power of 3 because of the coefficient, and then phosphate 3 minus to the power of what? 2, right? So that's going to be our solubility products for both of these. And these come into play because when we look at the molar solubility and we want to calculate KSP, we have to set up a relationship between the two. All right, so we have one other example. We'll skip that one. So here we have one where we're going to calculate the molar solubility, which is what you guys have to do for the lab we did last week, and then KSP. So given the solubility of silver chromate, right, in water is 0.022 grams per liter, calculate KSP for this solid. Right, so the first thing you have to do is calculate the molar solubility. Right, and the second thing is to set up an equilibrium table, which will then let you calculate KSP. So your example that we did in lab was a lot easier, right? Because our lab example, the reaction was KHT, or H2T, solid goes to HT minus plus K. Aqueous, right? And so we get a one-to-one dissociation there, right? The stoichiometry is simple, so it's easily comparable to the solubility. Here, you're going to have a little bit more difficult, not more difficult, a little bit more work to do when you calculate the molar solubility. So how are you going to calculate the molar solubility, right? If we're going to set up an equilibrium table, generally we do that in units of concentration, right? So if we're calculating the molar solubility, you're given that the solubility is 0.22 grams per liter. And so the way you interpret this is that you can dissolve 0.22 grams per liter of water. 0.22 grams of silver chromate per liter of water. So how would we get the molar solubility in units that we can use? Right, and that's going to be moles per liter. Right, this is what you solved for, or what you this is the first thing that you did in your lab last week, because this is what you determined when you did the titration, right? The moles of sodium hydroxide that you use equals the moles of potassium tartarate in your saturated solution, right? That's exactly what you determined in your lab last week. So you started off from this value. The only thing is you didn't have grams per liter, you had moles per liter already. So how do we go from grams per liter to moles per liter? How do you go from grams to moles in general?
Oh, it's grams divided by molar mass.
Yeah, the molar mass, right? We use the molar mass to do that. Right, so you use the molar mass, and you know you can get the molar mass from where? The periodic table, right? So why don't you guys take a second to review to see if you can get the molar mass of silver chromate. You see your periodic table up there, you can use that one. Right, so if we have a molecular compound, it's just 2 times the molar mass of silver plus the molar mass of chromate, because we only have one of them, plus 4 times the molar mass of oxygen. Right, so we get the molar mass. What'd you get?
331.6.
Yeah, 331.6 is fine. And that'll be grams of silver chromate per mole of silver chromate. Right, and so if we have this value, 2 grams per liter, this is silver chromate, we can convert that using the molar mass, get 331.6 grams silver chromate per 1 mole silver chromate. This is a long molecular formula to write each time. The units of grams cancel out, and we're left with moles, which is what we want. This isn't equal to, this is where'd that G come from?
From the AG.
AG, oh, okay, I was like, I don't see any grams anywhere. Okay, yeah. Right, and so what did you get for the molar solubility when you did this? It should be some small number, like 10.
6.6 times 10 to the negative 5.
6.6 times 10 to the minus 5 molarity, right? So this is our molar solubility, right? We need to relate this to KSP. KSP says at equilibrium, this is the concentration of whatever the solid is in solution. So we're going to set up an equilibrium table to then relate this molar solubility to the, right, so now we need an equilibrium table for the dissolution, right, so which means we need a reaction. We have Ag2CR4 solid is going to go to, what is going to be our products in this case? 2Ag plus aqueous plus CrO4 aqueous 2 minus. Alright, so that gives us the stoichiometry. Again, our molar solubility was 6.6 times 10 to the minus 5 molarity. Just put MS for molar solubility. And we can set up an equilibrium table here, right? So if we start off with some initial amount, we don't have to say any specific initial amount. So we don't have to worry about the initial amounts here because we're given some amount that is corresponding to the amount that's going to be dissolved in a saturated solution. So the change, though, we can write, and then we can write our equilibrium concentrations. What about for solids? What do we have to do with solids and our equilibrium constant?
Just cancel them out.
We don't worry about the solids at all, right? Technically, we would be minusing some change here because we're dissolving the substance. And what's the change for the products? Are we going to be minus or positive for those change? Those should both be positive, plus and plus. And then if the change is some arbitrary value x, then what would it be for silver and chromate? It'll be 2x, and then chromate would be just x. So then our equilibrium values, we don't worry about the solid. Why? Because it doesn't go into our solubility product or equilibrium product in general, or equilibrium constant in general. So we have 2x and then x. So then KSP is equal to Ag2 plus squared CrO4 minus. The equilibrium values for these are related to our new equilibrium concentrations, which is 2x squared and then x. And so now we're kind of stuck at this point, right? We want to solve for KSP, but we also have these two unknowns. The only other thing that we're given is the molar solubility. All right, does anyone remember what the molar solubility was equal to in our lab? It was a concentration of what? It was the potassium tartarate. It was the concentration of that substance in solution. So X is going to be equal to the concentration of Ag in solution, right? And the molar solubility is what gives us this value for X, right? So the important thing to realize here is that this is equal to your equilibrium concentration if you're given the molar solubility. Because it doesn't matter how much we start off with, which is why we don't have anything in the initial row here, right? We know that the maximum amount is related to this, right? So if we have some arbitrary volume, right, we don't care about what the volume is here, then we know that this will be the concentration of whatever it is that we dissolve in solution. Anything else is just going to crash out. It's going to stay solid, right? So this is going to be the concentration of that value. So this is equal to X, which means to calculate KSP, all we have to do, where's my create a new page? Am I good to go on to the next slide? Is anyone still writing? Is I plug in KSP is equal to 4 times 6.6 times 10 to the minus 5 cubed. Where'd the 4 come from? Yeah, because here we have 2x squared, right? Which means that that 2 gets squared, so we get a 4, x squared, x to the 1, x to the third. And so then the KSP value for this should be 4 times parentheses 6.6 times 10 x to the y 5 minus and parentheses cubed. Why would it not give me 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 1.15 times 10 to the minus 12. Right, so that's how we would solve our molar solubility constant. So what's different from the solubility compared to the equilibrium and the ice tables we were looking at before is just that the molar solubility is related to our solubility product because it's the concentration of each of the individual products in your reaction at equilibrium. And that's because that value tells you the maximum that you can dissolve for a given volume. And the maximum that you can dissolve at a given volume is just how much you will dissolve for any initial given concentration. All right, any questions on that? All right, so the same idea with the equilibrium table, the arbitrary change is represented by some variable x. Keep in mind the stoichiometry for what that change is going to be. And then we just plug in values. So here we don't have to use any ice tables or anything like that as well. Okay, so what about this question? We have a molar solubility for magnesium fluoride, right? Or we have a KSP for magnesium fluoride, and we want to find the molar solubility, right? So here we're given KSP, and we want to find the molar solubility. And what was that equal to in our last? Right, what was molar solubility? What did we say that was equal to? What was kind of the realization for that one? It was equal to x, right? So this was equal to x, which is the amount that's dissolved at equilibrium, right? Because we start off with just all solid. This is the amount that's dissolved at equilibrium. Right, so how do we then write our expression? Right, we have our initial change in equilibrium. What's going to be our change for each of these? Minus x. What about magnesium? Plus x. And then fluorine ion plus 2x, so that gives us x, and then 2x. This we don't worry about here, we don't worry about that here. And I put a bar through this last time. Technically, this would be 0. Both is what you're starting off with, right? As you put the solid in the water, you start off with 0, and then you make some. And so then what's our expression for KSP in terms of the concentrations before we put in x? It should be the concentration of magnesium 2+, and then fluorine to the power of 2 because it has that coefficient, right? In terms of x, which is our equilibrium concentrations, right? These, what is that equal to? 2x squared times x, or in the other order, I'll put it. X, and then 2x squared. Which means, again, we get 4x to the third. And what are we solving for here? The molar solubility, which is x, and then we're given this value already, right? So to solve for this, we just have to solve for x here. So we solve for x because it equals the molar solubility. So we have 7.4 times 10 to the minus 11, 7.4 times 10 to the minus 11 equals 4x cubed. How do we solve for this? Divide both sides by 4. All right, 4 cancels out on this side. We get x to the third equals 7.4 times 10 to the minus 11 over 4. And what do we do from here? We cube root it, yeah. So it's called a cube root, which is the same thing as just raising both sides to the 1/3 power. Right, so in your calculator, you can just put 1/3. Usually calculators have a cube root button, but if it was, to the power of 4 or something like that, you would have to change that, right? Because our exponents is x to the a to the b equals x to the a times b. So this simplifies to x to the 3 times 1/3, which is equal to just x to the 1, right? That's why we cube root both sides. So that gives us x is equal to 7.4 times 10 to the minus 11 over 4 to the cube root. We plug that in. It's already a small number, so when you cube root it, that exponent should get larger or less negative. So we get clear. 7.4 divided by 4 times 10 exponent 11 negative n parentheses exponent parentheses 1 divided by 3. Enter. And I get 1, 2, 3, 4. 1, 2, 3, 4. 2.6, bless you. Or was that a cough or a sneeze? Okay, then I take it back. 10 to the minus 4. Right, this is, in this we know is in units of what? What does X represent here? Yep, moles over liter, right? Because the molar solubility. So we know we're solving for that, so that has to be the units. So it's just in units of molarity. We can also rationalize it because we use an ice table to solve for X, right? And that's looking at change in concentrations. So this is the maximum number of moles you can dissolve per liter for, I don't know why the resolution went down just for that alone, for magnesium fluoride. Right, this is the max number of moles per liter we can dissolve of MgF2. Right, and we can rationalize that because if we look back at our ice table, even though it didn't come into play for our equilibrium, that's how much we lose of the solid, right? X here is how much we lose of the solid itself. It's the maximum amount that we're going to dissolve when we reach equilibrium. The only way we can dissolve more or less is if we change the temperature, right? Because that changes KSP. All right, any questions on this? Right, so molar solubility, solving for KSP, and going between the two, it's relatively straightforward. We just have to realize that what this variable X means in terms of dissolution is the amount of solid that we're dissolving in the solution itself, right? So there's two kind of variants for this problem. Either you're given the molar solubility and solve for KSP, or you're given the KSP and you solve for the molar solubility. And both of those just involve setting up an ice table just to get an expression that relates those two things, right? So the main idea is just relate KSP and X. And this was our molar solubility, remember. X in this case is molar solubility because at equilibrium, that's how much of the solid we're losing to the aqueous phase. And so now we can start to think, okay, how does this relate to what we're doing in lab, right? We're doing a lot of selective precipitation, which means that we're dissolving some solid, or we have the ions already in solution. We want to get them to crash out of solution. We want them to go the opposite way in this reaction. So what we're going to start talking about next time and a little bit right now is that if we have some other ion in solution, that'll affect the equilibrium. Meaning, if I look at this reaction, and let's say I add a bunch of another salt that has fluorine in it, right? If I add a bunch of salt that's more soluble in water, and that means I add a bunch of fluorine ions to the solution, what's going to happen to this reaction? It'll shift that way, which means that I'm going to start crashing out all of my magnesium in the form of a fluoride ionic compound, right? So everything that we're doing in qualitative analysis, I know it seems a little nebulous right now, is we're just adding and removing stuff using Le Chatelier's principle, then shift these equilibriums to get some stuff to crash out and some stuff to stay in solution. And it isn't just as simple as, well, I'm going to add fluorine, right? I might have this reaction, then another one where a complex ion, like our first lab, if you guys remember the color change, right? That was a complex ion. If that's forming, that could be taking away the fluorine ion to form a complex ion. And if I'm taking away the fluorine ion, what happens to this reaction? Yeah, now we're shifting it to dissolve the magnesium. So maybe we had the magnesium in a precipitate, we want to dissolve it again. we add something that forms a complex ion with fluorine, it removes fluorine from this reaction and causes this dissolving of fluorine, right? So everything that we're doing in lab is related to this shifting of reactions, solubility, and then equilibria, right? So try and keep that in mind while we're doing everything. We have like 3 weeks of that, so we'll be going over it in a little bit more detail at the beginning of each lab. All right, so we'll wrap up there for today.